The broadcast is now starting. All attendees are in listen-only mode.
Hello and welcome to our webinar, The Future of MBSE with Requirements in the Loop. My name is Noreen Klinga, Channel Marketing Senior Manager in North America for Dassault Systèmes, and it's my pleasure to be your moderator for this presentation. Today's session is the second in the series of MBSE webinars specifically created for the high-tech industry. You'll be hearing more about this shortly in the presentation. And before we begin, I'd like to mention, oh, there they are. So this is number 2, and we'll talk about number 3 later in the presentation. Before I begin, I'd like to mention that although attendee phone lines are muted, if you have any questions during the webinar, please submit them via the questions window located in the GoToWebinar control panel, and we'll address them at the end of the presentation. Also, this session is being recorded and will be available on demand. With that, I'm excited to introduce our presenter, excuse me, Yves Genevaux. Thank you. Dassault Systems Engineering Learning Experience Expert, who will provide an introduction to Dassault Systèmes' unique requirements in the loop solution. Over to you, Yves.
Thank you very much. I apologize for having such a complicated and so Frenchy name. I'll be your host today. I've been working on during many years on tools for system and software engineering, and I'm on this topic, requirements engineering, simulation, validation, test automation for 6 years now, and 2 in Dassault system. The innovation we bring is to bring into the classic MBSE model-based system engineering. We bring also the requirements which were sort of 2 separate domains. You could hear people talking about the model on the one hand, requirements on the other hand, and as you will see, we merge that into one model, which enables to make a very powerful validation of the functional specification, but also to automate radically the test on the way you probably never saw before. So that's a strong statement. I will have now to deliver if that vision is true. A few words on the company, Dassault Systèmes first. It's a company where we share a very strong vision about innovation. I'm enjoying to work with many passionate people all over the world. We contribute to innovation through our clients and partners in many domains, from mobility, high-tech, avionics, defense, pharmaceuticals, etc., etc. So we are really afoot in many innovation domains. We come from a long story with the 3D tool CATIA. We started on the 3D design many years ago, and then of course systems aren't just made of shapes and mechanics and pieces of metal, but also of course today they are very complex with embedded software, electronics, etc. And so progressively over the year, the Dassault system portfolio has grown to be able to provide global solutions to the client, with a very strong moment with the introduction of the 3D experience almost 10 years ago, to ease the collaboration of many engineers in a company. Today, for our discussion today, I will first start presenting the pains, the challenges that we address with our solution. Then I'll speak about what means a model-based system extended from the beginning to the end. It's a dimension that is often missing, I feel. And then I will present you and demo live the Stimulus tool. To finish, I'll mention a few stories coming from our clients to illustrate what you could do tomorrow with such a solution. And when I say tomorrow, we are Thursday, that could be Friday, actually, you will see. And we'll finish with question and answers. During the session, we'll do some polls. So we'll have a few questions to ask you, and we'll review together the results by the end of the presentation.
Yep, and I see our first poll is up.
Shall I continue?
Yes.
So please feel free to answer, and so we can share together these results in 45 minutes. So first, about the context, what are the challenges that we address? Actually, you can identify the early phases of embedded systems with two slightly different steps. The first step is a pretty high level. With complex system, you can't afford to get into every detail immediately. So you need to remain at a pretty high abstraction level. And later on, there is often another team who's going to get into all the details of the system, building a sort of to-do list for the guys who will implement the system, possibly develop some software, and also create the validation plan. In that detailed specification, you cannot miss anything. And so there are two slightly different objectives during this early phase, which is, at first, you need to remain at a reasonably high level of abstraction. And second, you need to go into every detail and typically, pretty traditionally, write many requirements in a requirement management environment. And for us, that's mostly where Stimulus will focus, that detailed specification phase for embedded systems. So we're going to see embedded system as sort of blocks, objects. It could be a software function, and they receive inputs, you produce outputs, and Stimulus will be about the functional requirements, the definition of the expected behavior. It's basically the relationship between inputs and outputs, as you can see an example here. So this is going to be our focus. And when you look into the industry, it's a phase that is hardly under control. 70% of the errors created during a project, they are in the requirements. And only 4% are detected through the traditional way, which is reviews. So in a nutshell, reviews don't work. Writing requirements in natural language is a great way to create a lot of problems. In our experience, when we look at pieces of specs, wherever they're coming from, more than half of the functional requirements have issues, are problematic. We'll see the kind of problems we identify. So it's bad news on the one hand. It's also very good news, because it means that should you find a solution to address this topic, the gain is huge. A second pain is if requirements are written with a natural language, then you can't generate anything. It means that each and every functional test case must be created manually. And that's a very big challenge. It's actually duplication of information. And you never know if at the end, the test case, which is supposed to be used for the validation of the system, is actually a fair reflection of the requirement. It could be something else, actually. And it's painful. It's difficult to develop. You never have enough test cases. Therefore, the validation is not strong enough. Bugs remain undetected, etc., etc. Any of you who have been involved in projects know that. So these are difficult challenges for which there were no solutions so far. So how can we pretend to change anything to this? In Dassault Systèmes, we have a pretty known tool, previously called the Magic Draw Cameo. Now it's called CATIA Magic. And it's going to cover these early phases of the development where you don't want to get into all the details. So that's the blue part, basically. And we have smooth transfer of data to go into the detailed of the specification of embedded systems with the CATIA Stimulus solution. So first phase, you don't want to get into every detail. Next phase, you do want to capture all the details. And it's not exactly the same formalisms that will be used, but we have the possibility from CATIA Stimulus to reuse data coming from CATIA Magic to ensure this digital continuity, which is very, very important to us. And we'll go, as you will see in the demo, we go until the end of the validation, until the HIL validation, hardware in the loop validation. Let's see how we address these challenges. So I already said, natural language requirements, it's problematic. We propose you to write these kind of requirements on a more structured way, basically, with language based on executable templates. And so it's almost the same as before, often simpler to understand, and that's going to give you simulation. You can simulate and make sure, observe executions of the system according to the requirements. That gives you the capability to validate the functional spec very early, find the errors in the requirements, and also, as you will see, to automatically test that the system, the developed system, meets its specification. So on the left-hand side, you see that we make sure the spec is correct, simulating the requirements, and may possibly verifying they meet safety requirements. I will show you that in the demo. And later on, once you have developed a system, maybe a piece of code or something more complex with hardware, we're going to reuse the spec, observing the execution of the system. The system is stimulated by stimulus. I'll get back to that. And any violation of the spec during the execution of the system is detected. That's why virtually a sentence could be almost, you got nothing to do to test that the system meets its spec. Once you have a specification in stimulus, you already have everything you need to do the validation of the real system. I'm, of course, focusing here on the function aspects. You have other test objectives, of course. So these activities will still be there. I mentioned that you create the requirements based on templates. Stimulus comes with a language, which is actually customizable, extendable, and you combine, as I will show you in the tools very soon, you combine the templates to create the sentence you like, and then click on the play button and simulate, and look how the system behaves according to this requirement. It's as simple as that. Now, systems aren't just made of a few requirements. Our users create, aircraft, train signaling systems, missiles, cars, nuclear plants. So they are complex systems. They need to be able to catch the architecture, possibly inherited from the work, from the modeling work made earlier with CATIA Magic. And so a spec in Stimulus is a certain hierarchy of block diagrams. And when you want to define the expected behavior of the block, then you can write textual requirements and or state machines, or a free combination of both. Simulating a spec means you send inputs and observe the answer. So in Stimulus, you will be able to create test scenarios, use cases, if you will, under the form basically of a set of constraints on the inputs. And out of this set of constraints, here combination of text and state machine, you generate as many test vectors, as many combination of inputs as you like. And so you can intensively run thousands of execution of the specification and help the analysis with observers, where you would typically put very important properties, safety goals, whatever, safety properties, safety requirements. So you want to know that none of these executions will violate this particular property. So that's a very, very strong way to stimulate and verify if a given specification is correct. And we'll do the same with the code later on. So in other terms, here it's another representation of the same thing. A test scenario in green, from which you send stimuli and execute the spec. Possibly in an observer, you can see this eye symbol. You put any property you like, get it running, and observe when you have a violation. I got a second question for you, for the poll. So I'll leave you a few seconds on that. And we'll continue. So the previous slide was about testing a spec. Now it's testing the code. We use the same mechanism to test the code against the specification that you would have put in an observer. Or if today you don't have any spec, you could take 2 minutes to write a safety property and stimulate intensively your system to see if that property is violated sometimes. So it's practically the same as before. That's why I said you got virtually nothing to do to test a system against its spec. I mentioned you go up to the final test of a system, including the hardware, and that's what you see here. In hardware in a loop environment, you can record the inputs and outputs that happened during the tests, load these information into Stimulus, and we got everything we need. Remember, requirements are a relationship, an expected relationship between inputs and outputs. Therefore, if you give the inputs and outputs that happened during the test, Stimulus can tell you if any of the requirements has been violated. So it's a post-test analysis for the log file. This is very effective. That's a very difficult task, actually. From these slides, I hope I was able to explain that Stimulus is about authoring, creating the requirements, simulating and validating them. It's not about requirement management. Dassault Systèmes requirement management is one of the facilities offered by the 3D Experience platform. We have a synchronization mechanism between both, and many of our users also use different environments, doors, PTC, you name it, and we can exchange through Excel sheets between classic requirement management tool and Stimulus. That works nicely as well. A third question for you. And now I'm supposed to show you that this tool indeed exists. For the demo, I'll use a small example. Don't be misleaded. Of course, it's a small example, reasonably simple for pedagogic reasons, so you understand how the tool works, how you could use the tool tomorrow, next week. Of course, as I said, actually people use Stimulus on very complex systems. So that example will be the headlights of your car with an automatic mode. So depending on the light intensity, the headlight's going to be on and off. And you probably know that if you have one limit, you're going to have issues near the limit. So you got to create hysteresis on many topics for embedded systems. So here we're going to say that when the light intensity goes under 60% for 2 seconds, switch on. And wait until you're above 70% for 3 seconds to switch off. So let's go into Stimulus and see how this kind of system could be described through a set of requirements. So to warm up, we are in Stimulus now. Let's look at the on and off modes. You can see here maybe requirements that existed already and imported from the requirement management environment. It's plain text appearing as a comment, and you would write the equivalent in the Stimulus language. When the switch is on, headlight shall be on. You see here on the right-hand side the inputs and outputs of that particular system, and they've been defined in a glossary where, for instance, you see the switch has 3 values: on, off, auto. How do you write requirements in Stimulus? Most of the time, the users, they are like me, pretty lazy. They're going to do copy, paste, and change some parameters. For instance, saying off here, and the Stimulus will complain here because that's not a legal value. Actually, we need capital letters. You would do a lot of copy paste. It's going quite fast. Many requirements have the same structure, actually. Otherwise, if you want to create something from scratch, I would go into the library of templates and drag and drop the elements I need. So I need a when. I go in the temporal library, drag and drop when. Same for is and shall be. It's actually equals. Let's go in the logical library, drag and drop twice equal. Now I get everything I need to create the second sentence. So I'm going to write when the switch equal off. And I put this into the condition. And then headlight equal off, copy, paste, drag and drop. Done. We got 2 requirements. I can simulate them. You might want to see not an equal here, but the shall whatever. So I could right click and choose another appearance, like shall be. Here I might choose the format is. Doesn't change anything to the semantics, actually. So we have 2 requirements. Do they reflect my intention as a system architect? Let's click on play and see how the system could behave according to these 2 requirements. I ask Stimulus to generate some steps. You can see in green inputs generated automatically by Stimulus. We have not yet defined any test scenario, so it's random inputs. And in red, you can observe the response of the system according to the spec. Here, 2 requirements. So when the switch is off, headlight is off, according to this requirement. In gray, you see the one that is inactive. So we animate the requirements. Next cycle, switch is on, headlight is on, cool, that's what we wanted. A bit further, you see dotted lines. What do they mean? They mean that a Stimulus can tell that the output is unconstrained. You see its headlight is free. Why is it free at that point? Because all the requirements are inactive. And of course, it's because the switch is equal to auto. There's no requirement for the automatic mode. Stimulus is the first tool helping you to find the holes in the specification, the moment where you're probably missing some requirements. Let's see a more complete piece of spec, the version 1 here, with a set of requirements for the automatic mode. Here, you see 3 requirements. I remind you what we're trying to do. We are trying to do this. And so you can see when light intensity is less than 60 for 2 seconds on, above 70 for 3 seconds off, and in this hysteresis zone, maintain. When I'm demoing Stimulus, I often ask the audience, okay guys, so today you do reviews. Would you tell me if, let's do a review. Does this specification meet our goal? According to, will the system behave as planned? And in general, I first get an amazing silence for a while. It's not easy to answer. Already 3 requirements like that, running in parallel, and parallel is the key thing. It's already difficult to say if every situation is going to work properly. The human brain is just not made for that. So let's test this version in Stimulus. So I'm going to use a test environment. So you see a small block diagram here. In that block, what I did was to simply drag and drop the spec V1. It receives inputs generated from these ones. And in these blocks, I'm just putting some constraints to constrain the inputs. So for instance, here, I got one called Force Auto. It's very simple. I want to focus on the automatic mode, at the beginning at least. For the other one here, I'm going to get the light go up and down. This allows me to illustrate. So that's the scenario. It illustrates the capability of Stimulus to generate many, many different kind of input signals for one given scenario like that. So if I click on this, I can have one first test vector. Let's make one test vector for 400 cycles. Here I defined a cycle to be 0.1 second. Click on this button and off you go. You have here a light intensity in red profile generated automatically from the scenario you have here. And you can see if I'm, for instance, at this moment, I'm currently making the light intensity increase under the constraint of which is here. And if I move, Stimulus is going to choose another target, random. And now I'm going towards this target. There are billions of ways to generate stimuli or a test vector out of such a scenario. So if I click on the button, I get another one and another one, or 10 in one shot. And all these test vectors could be exported to CSV in order to be reused in other environments, implementation environment, model in the loop environment like Simulink, etc., or in the HIL environment. So a very strong capability to generate many, many, many different combination of inputs on a controlled manner. Let's go back to our test environment. Explain to you the 3 boxes. So let's test the version 1. We're going to make one execution, 400 steps. So what do we observe? Let's double click in the blue box. So we can see all the requirements animated by Stimulus. You recognize in blue light intensity going up and down, generated by Stimulus. Green is the switch, doesn't move. We fixed it to the value auto. I added these 2 variables to visualize the limits of the hysteresis. And we get headlights sometimes on, sometimes off, and sometimes blinking. So let's see, for instance, if I'm at this moment, light intensity is 57%. This requirement is active. Therefore, headlight is on. Let's go to this moment. We are in the hysteresis zone, 65%. We maintain headlight to the value on. If we are here, headlight is unconstrained. None of the requirement is active. They are all gray. And therefore, headlights are blinking. Until this moment, where after 3 seconds, this one wakes up and will switch off the headlight. So we realize, okay, we are missing, we have forgotten to define what the system is supposed to do during the 3 second period, and the same here for the 2 second period, which is here. So, right, so we forgot one requirement or some requirements. Let's look at the version 2. We have one more requirement here, which says when you get out of this hysteresis zone, after a change, don't change. So normally we should not have this blinking phenomenon anymore. So let's test the V2. I'll drag and drop the V2 into the blue box and click on play. One execution again, and we can see that we improved. We don't see the blinking phenomenon anymore. Let's do more tests, and that's automatic. Click on play, you get another execution, and another one, and another one. They seem to be pretty okay, but at the 5th execution, we have this red vertical bar, error messages here saying you got conflicting requirements. There are contradictions in the requirements you gave me. I don't know what to do. If we open the error messages area, we will see, all right, at the time of the error, we got headlights shall be on working, and also headlights shall be stable. And the shall be stable is actually trying to maintain the value off. So it's the conflict with this one. And it's not obvious. And it's only 4 requirements. So if you take any component of an embedded system, any function, you got 1-2 dozens of requirements for something, it's already too complicated to be reviewed and assessed as, yeah, it's going to work. I made a review, it's going to work. No, you just don't know. Without a tool, it's virtually impossible. Let's call it an extremely difficult challenge, to be polite. But making sure that a piece of spec is correct is without a tool is doubtful. Anyway, let's move on. That's a version 3. It works. We made a lot of simulation. You're happy with it. Many of you have a need for making sure that some properties are never violated. Maybe it's safety requirements. So how can you make sure that a piece of spec, here a set of textual requirements, but again, it could be a block diagram with many requirements in each block, etc. So it can be a very complicated piece of spec. How can you make sure it won't ever violate a safety property? Again, if it's natural language, which is the case of all of you today, we're going to call it an extremely difficult challenge. How could it be better with Stimulus? Let's see. I'm going to put the V3 into my blue box, create an observer with the I symbol, name it safety on Thursday. And I'm going to put a property inside this paragraph. I've got a set of properties ready here. I could just enter one directly. I'm going to use one that is here. When the switch is auto, headlight shall not blink. So this is my important property. I want to make sure that my version 3 will not violate it. So I just drag and drop this property into the observer. Done. If I now simulate, execute the version 3, let's do it 20 times in one shot. What we are looking at is not so much the executions here. Imagine you have made already many simulations and you're happy with it. You watch the color of the observer. Green means fine. Obviously, we never violated the observer. 20 doesn't mean much, but if it's 20,000 execution of a piece of spec, never violating a safety requirement, you start to have a strong level of confidence, which is pretty interesting. And I invite you to think about how you proceed today. Let's move on. Now we got a very good, trustable piece of spec, very strongly validated, meets the safety. We can give it to the development team. They're going to create a system, piece of code, maybe even with some hardware. And you want to test that the system meets the spec. So you're going to go to your validation team, give them on the one hand the spec, on the other hand the code. And what are they going to do? Are they going to start testing? Absolutely not. They are going to open the requirements, scratch their head, start to create painfully each and every test case, and we'll be looking for the guys who wrote the requirements because they are very, very complicated. While that traditional validation team is sweating, what could you do if you had Stimulus? See here, I have a DLL, it's just manual code compiled. It could be a FMU, functional mockup unit, generated. So it's executable code generated from many environments such as Simulink, SCADE, Control Build, you name it. So I have an implementation basically here, which I can just put into my blue box. I just need one thing before I execute it. I'm going to create a second observer, which I will name spec observer, in which I'm going to put the strongly validated spec. That's it. Took me 20 seconds. Click on play, execute 20 times the implementation, the code here, and observe if or not we respect the spec and the safety. Answer is yes. It's the code. Let's look to the coverage of the specification. So during these 20 executions, I covered 37% of the spec. Of course, you could open the spec in order to access to the requirements which have been properly covered, this one, the auto one, and those which were never covered, for instance, this one, 0%. It's the on requirement. Same for the off requirement. Oh yes, you remember, we put switch equal auto all the time. So let's give a bit of freedom to Stimulus to change the switch every 4 seconds. So I change the scenario with a drag and drop. It's a very simple one. And now I re-execute the code against the spec, against the safety, completely automatically with more diverse inputs. And this time, I got a violation of the spec. So there are 3 questions you should wonder. Which execution violated the spec? When? And which is the violated requirement? So we're going to answer to these 3 questions in one shot. Click on the error message. The execution number 1, so actually the second one, violated the spec at 28 seconds precisely, and this is the violated requirement. When I say you got nothing to do to test that the code meets a spec, that's it. There are more features in Stimulus with automatic testing campaign, etc. But as an appetizer, I think that's quite all right for the time being. So let's go back to our presentation. So how do people start with such a tool? Are they going to look at their huge database of existing requirements and start to sweat for years? No, 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 no. You apply Stimulus on the new stuff, new components, new system functions, whatever. And at the end, it's always a set of components. Maybe there are many, but at the end, it's objects defined with a dozen or maybe 2 dozens of requirements, not more, because you wouldn't understand anything anymore. And you got this example from the automotive industry, 20 requirements defining a safety critical function. We put them into Stimulus, nothing works. Nothing, it's not special, you know. I didn't took the worst case we saw ever. No, no, that's our daily life. 2 days to make it work properly. Is it worth it? Hell yes. Another interesting usage of Stimulus is when you got a problem from the field, something is not working. What are you gonna do? What do your colleagues do? They look at the code and they start debugging the code, trying to figure out what's wrong. And you remember, most of the time, the error is not in the code, it's in the spec. Why are they looking at the wrong artifact? Because they have a debugger. But it's not because that's probably where the error is located. So in that story, couple of days to capture the spec, simulate it, make it work properly, and then 1 week to rewrite the code from scratch. Automatically, you just saw why it was so fast until they were able to deliver actually the New York City Metro. And they saved 20 million euros penalties. So a few takeaways, few ideas I'd like you to carry with you, and please continue to engage with my Dassault Systèmes colleagues if you would like to check if this is really something that could work for you. First, you can now, for the first time, make your functional specs for embedded systems, that's the domain, working properly from the beginning. That was not possible until Stimulus. The gain in testing is huge. I want to insist on that. The previous company in the railways industry, they used to do 2 test campaigns per month. They are doing 2 test campaigns per day with Stimulus, 20 times faster. So the functional test automation is really, really very strong. And you can apply that tomorrow for some first components where you have a dozen of requirements, and you are going to find a lot of issues already, bringing you a lot of value already tomorrow. I mentioned some of my colleagues located in the US with whom you can, of course, interact. But we have time for questions.
Yves, I'm wondering if we want to share the poll answers first.
Absolutely, yes, yes.
Let's go ahead and do that.
So I'll let you mention that.
Yes. So the confidence level on functional requirements quality seems to most range in the medium. Most listeners said medium. to low for poll question number 2. Coming right up. Do you have to verify if your specification complies with some safety critical requirements? It's split 2/3 said often, and the remaining third said sometimes. And finally, poll question number 3. When do you detect most of your requirement errors? It seems that a quarter of the people said at specification time, a half of the people said at testing time, and the remaining amount said at validation time. So thank you, Eve. That was a great overview. If you have any questions, please submit them now in the questions window on the GoToWebinar panel, and we actually have a few that have already come in. So the first one asks, are we able to connect CATIA Stimulus to any CAD model and simulation tool for testing?
Yes, so not CAD model per se. So here we are really focused on the command control part of embedded systems, mostly implemented with electronics, or and most of the time, software. Do we collaborate with other tools? Yes. For instance, if I take tools such as implementation tools, basically design tools such as Simulink, Skate, who generate code, for instance. We first import and test an FMU, so executable code coming from these tools, into Stimulus pretty easily, as I showed to you. And another possibility is, say you're using a tool such as Simulink. Today, you got to create each and every test case manually in Simulink, which is annoying. You could export the test scenario from Stimulus into Simulink as an FMU. So you generate many stimuli in the Simulink environment automatically. And also the spec or some properties you want to put into an observer can also be exported as an FMU into Simulink. So in that way, we sort of enrich and make other tools such as Simulink, Skate, Control Build, etc., tools that support the FMI standard, much more effective in the simulation.
Okay, great. We have a second question. In the headlight model, it looks like noise is included in the light stimulus. Does the capability to simulate noise level or degree, of damping?
Yeah, cool question, thanks. So you see here, we have generated for the light intensity, we generate a certain profile, possibly with some noise inside the signal. And in the stimulus library, you have many ways to access to many mathematical functions that you could use to generate pretty complex signals profiles. You can also load into Stimulus using a CSV format. You can load into Stimulus signals that you already recorded coming from other tools that are already in place, and you would like to reuse these signals profiles, these test vectors into Stimulus. That's also possible. So create them outside, import them into Stimulus, or use these many functions to generate the profile you really would like.
Okay, very well. Well, I see we're nearly done with our time today. So once again, I'd like to thank you, Eve, for your time and expertise, and I hope the audience found this session informative and it sparked some ideas. While we're waiting to see if any other questions come in, as Eve said earlier, to learn more about what we were speaking about today or MBSE, contact Eric Bololini and Derek Stratton from Dassault Systèmes. Their email will be shortly shown on the screen. And I'd like to just remind you that at the start of our webinar, we mentioned that this was the second in the series of MBSE webinars specifically created for the high-tech industry. Our next one will be on April 1st, when we examine end-to-end traceability in a heterogeneous and dynamic environment. And you'll be receiving an email invitation on that shortly. Finally, please take a moment following the close of the webinar to provide some feedback to us regarding the information presented today. Your responses will assist us in developing future webinars on topics relevant to the high-tech industry. Once again, this presentation has been recorded and will be available on demand. Thank you for joining, and this concludes our webinar.